So, hi again, I'm Nick Marchuk, and this is the second of 3 videos on designing a printed circuit board using Eagle. In the previous video, we designed an Eagle library with all of the components that you see in this schematic. And in this video, we're going to take that library and redraw the schematic. So, let's begin. I'll go into my control panel in Eagle, and I will find my project. So I called this ME433-video. It has my library inside. I'll right-click on the project and say New Schematic. First thing I like to do is save it so I can give it a name. And then we have to add the library to this project, the library that we just made. Oh. Just unplug my computer to hopefully make the audio a little bit nicer. Okay, so I'll go to Library, open Library Manager. And if I go to the Available tab and browse, I should be able to find my project and select my library. Once it's found it, I can click Use, and now the parts in that library should be available to me when I click the Add Part button. So, if you haven't noticed, Eagle's a little old school in how we do things. So if you want to add a part, first you go to the Add Part button, and it will open up all of the available libraries. And I'll go to the library just added, and I'll find my pick, and I'll add the pick. And then because I'm still in dropping mode, if I clicked again, I would add another pick. Not interested in doing that anymore, so I'll click Add a Part. And we're just going to go through and add all of the components that we want. So why don't we start with the battery? That's one way that power gets in. And the battery would go to the slide switch. And the slide switch would go to the voltage regulator. The voltage regulator would be providing power and ground. Also, I can use the USB to UART to get power. And I need to be able to program the PIC using the Snap Programmer. And I'm going to display some data on my display. I'm going to have some LEDs. So I'll have a power LED and a user LED. So this is the interesting part. All of my previous components, when I added them, there's only one footprint to use. Now for the LED, I have many footprints. So I'm going to select my LED and which specific footprint I want to use, which is the 3mm one. So it'll look like that in the footprint, but all the LEDs, regarding on which one I click, they all have the same schematic. Okay, so we'll have, maybe I'll stick over here, 2 LEDs. Each LED needs a resistor to limit the current. So going to REUS, all the resistors have the same schematic, but they have different footprints. So this can be a little tricky because the scale isn't super helpful here. Which footprint do I want to use? I'll try this one first. Unless I go down here. It does look a little big. Okay. Each LED gets its own resistor. Then I need 2 buttons. One is my reset button and one is my user button. And each of those gets a pull-up resistor. In this case, I'll just copy those resistors that I already have. So how do we make the connections? The connections are called nets, and the tool to use is called the net tool. You don't use the line tool. The line tool will let you draw lines, but that's not how you make electrical connections. You use that using the net tool. And let's see, I like my battery connector to kind of face the right, so I'm going to grab the mirror tool and just mirror it. And the top connection is ground, so I'll need some ground and power and those kinds of connections. So let me go back to add my part, and what I like to do is add one ground somewhere, and one 3.3 volts and one ground. And every time I need it, I'll just copy these. Okay. So using the copy tool, I'll copy my ground because my battery gets connected to ground, and I'll use the net tool to connect the ground pin of my battery to ground. Then let's just say right now that I want my battery to attach to pin 1 of this slide switch, and I'm going to connect pin 1 to pin 6 so that I kind of have this slide switch acting in parallel. Okay, and pin 2, go here. It's connected to pin 5, that's the output. So when the switch is in this up position, the battery will connect to the output, and that will go to V-in of the voltage regulator. And the voltage regulator is also connected to ground, and V out of the voltage regulator is always 3.3 volts. So I will connect the ground to the ground and the V out to my 3.3. That's how 3.3 gets out of the regulator into the rest of my circuit. The shutdown pin, I'm not going to connect to anything because I'm not really interested in being able to shut it down. Then the other option is I will have 5 volts from somewhere going to the slide switch. So I'll hook that up now. So in the downwards position, 5 volts, wherever it comes from, will be connected to the switch, which goes to the regulator, still making 3.3 volts. Now I have the option of powering off battery or powering off of a 5 volt supply. Now that I have 3.3 volts, I can turn on my power indicator LED. So from 3 volts, I'll go to my LED, which go to my resistor, and go to ground. And I should probably start giving some values to these resistors. So this resistor, I'll use 330, make it nice and bright. 330 for the other one that is in series with the resistor. And then my pull-up resistors for these buttons are probably like a 10K. Okay, why don't we flip over? Now that we have power, let's get the PIC to work. So how do we get the PIC to work? Every VDD of the PIC gets a 3.3 volt. And every VSS gets a ground. Did I miss any? There's only 2. Okay, and then the datasheet for the PIC says anywhere that there is a power, there should be a 0.1 microfarad capacitor. So let's go grab a capacitor. And again, you have to figure out how big is your capacitor. And the ones I've been using are actually 0.1 inch apart. It's pretty small. I'm going to use this first one. And then the V cap is a 10 microfarad to ground. So 3.3s go to capacitors to ground. V cap goes to capacitor to ground. And give these guys some values. So 0.1 microfarad. C3 is a 10 microfarad. Okay. A VSS is also ground. So C1, it appears, is connected to pin 28 and pin 27, but technically it's really connected to 3 and ground. So we'll have to remember when we do our board, C1 is actually supposed to be as close to the PIC as possible at these 2 pins. Even though technically it just needs to be between power and ground anywhere on the board. Same thing with C2, has to be as close to pin 13 as possible. Okay, sometimes I like to move these kind of further out. get out of the way in the future. Okay, that should be good. Okay, what else do we need to make the pick work? The snap has to be connected. The snap gets connections to power and ground. Then it has connections to MCLR and PGD and PGC. And rather than making very long nets that are going to twist and touch each other, I'm going to make them kind of stubby like that and then add a label. And then I'll name that label the pin name, so MCLR and PGD and PGC. And then the pins on the pick, I'll give the same name. And that's how it knows that they're connected. PGD, PGC. And then finally, the MCLR gets a pull-up resistor to make sure we make those connections. Pull up resistor and push the button to make it go to ground. And label the pull-up resistor wire MCLR. And I should probably give this button a value that is reset. Okay, my other button, might as well give that a label or value. This is my user button. Let's see, this LED is going to be red. This LED is going to be green. Okay, so the pick has power. We've got our power set up. We have the ability to program the pick. Let's get our user LED working. So that LED we're going to call user. It's connected to ground. Label that pin. Hard to see with this color scheme. What is this? We can call this A4. And then pin A4. And pin B4. Give them their labels. Okay, we've got our buttons, got our LEDs. Pick is powered. So the next step, let's get the pick to talk to our LCD display and to the computer through the USB to UART. We'll start simple. We'll do the display. So the display has a power line and a ground and SDA and an SCL connection. And here's our SDA and SCL pins. Now, lots of things talk I2C using the SDA and SCL pins, and I don't want to wire them direct like this and not give myself any other options to talk to them. So we add another part, our 1 part. So this is just a single hole. And give myself the option of more holes for SDA and SCL. So if in the future I wanted to add another part to my board, I could just solder wires to this SDA and SCL without having to like solder wires to the back of the board or something weird. Okay, so now we can talk to the display. Now we need some UART going on. So the UART, so the UART does not have 3.3. The UART is where we're getting 5 volts from. So this is the only other 5 volt connection. And a ground. So the UART, USB to UART chip can help give us power. And then we need connections to TX and RX. And we'll use U1 to make these connections. So U1 TX and U1 RX are the names that I'll use. U1 TX, U1 RX. So what are the connections on this side? Well, U1 TX goes to the device RX. So U1 TX outputs data into the receive of the USB to UART. The USB to UART TX transmits data out to U1 receive. Okay, now we can talk to the computer. So I think we've made all of the connections to make this board work. But what we're kind of missing is all the rest of the pins. So look at all the pins in the pic that we haven't used yet. Let's break those out to the sides of the board so that we have access to them. Those could either be wired into a breadboard, or it could plug into a shield, which is going to have other stuff soldered into it. So I'm just going to make labels for each of these pins that don't yet go anywhere. And then we'll use our 5 connector to break them out. And we can just use their names. Keep it simple. Got a B15, which later on will turn into OC1. So all of these pins have some other thing that they can do. And let's bring them out to the side of the board using the 5 connectors, and we're going to have 4 of them as shown here. One, 2, 3, 4. So these are the pins that need to go in very specific places on my PCB so that they will line up with the shield. So the purpose of the schematic here is to make sure we get them in the right order, because that's also important. If we get them backwards, then we might have a short or something. Lots of clicking. Lots of labeling. And then their placement was actually decided more on layout options. So I wanted to keep them kind of in order to make them easier to route later. So the actual layout here wasn't specifically made in any specific way, other than to keep the wires easier later on. So we're going to have B15, which is right next to B14, B13, B12, B11, and B10, B7, skip a bunch. Okay, so that's going to be like the right-hand side of my PCB. I also would like to get all my power pins out to the PCB. So we're going to use the next pin to send out V in, whatever the slide selector switch says our power is. Which I haven't labeled yet, so I'll go add a label to that pin to call it V in. Okay, so whatever comes out of that switch is called V in, goes to the regulator. It also goes over to the side of the board. Okay, then I was going to have a 3.3 volt line and a ground. Copy a 3.3, copy a ground. Okay, keep going down. B6, a V in, a 3.3, and then 2 grounds. Got more pins here than are necessary. Okay, A0. I think this one actually goes on top of the other one, but the orientation here doesn't matter. We just want to get the pins in order. .3 and then 2 grounds. Okay, so we've got the PIC and all the PIC connections that are necessary. We've got power going to slide switch and another power, 5 volts, going to the slide switch to the regulator to make 3.3. Got our connections to the USB UART and the snap and our display. We've got some extra holes going to our SDA and SCL pins. Let's do that somewhere else too, so we have extra access to power and ground. So I'm going to copy my one connector, and I'll give myself an extra power and ground and V in. Always nice to have lots of holes on the board. Just in case we made a mistake somewhere, we can cut a wire and then resolder it to one of these holes. Okay, so we can compare that to our master. These buttons. Okay, I think it looks pretty good. Now, the last step could be to run an ERC, an electrical rule check. So when we defined our parts, we had an option of making pins, specifically power pins, and these tags are power tags, so the ERC would go through and say, hey, this is a power pin. Did you connect it to a power tag? Now, I didn't define my parts in the library like that, so I'm not going to run the ERC, but that's something you could do. Okay, so the last step would be to click this button, SCH to BRD, and we'll generate a BRD for us. And I'll take all those parts that we made, dump them on the left, and then here's our PCB on the right. So I'm going to end this video here, and in the next video, we're going to move our parts onto our board and make the connections, and then generate the Gerber files and see how they look.